Welcome back to the instructional video series on hierarchy of energy theory, where we unify all physics under one physical model. I am your theory influencer, Scott Gordon. In these next few segments, I'll take you through the lengthy process required to reveal the internal structure of a photon, and how a photon comes to possess its properties. In this segment, we start our journey to find what light is by considering a wave within a one-dimensional space-time. We then look at the properties of this wave and see if we can relate it to our current mathematical representation of waves. We define the speed of light and introduce the concept of the relative constant. And to earn our first Nobel Prize, we answer the question, why is the speed of light the same in all inertial reference frames? If you don't think the answer to this question deserves a Nobel Prize, don't worry. There are plenty more opportunities coming as hierarchy of energy theory is advanced. You can be a doubting Thomas or jump on board. The choice is yours. Let's start where we left off in lessons 1 through 4. We showed that spacetime has an internal structure. Spacetime is composed of a building block, where energy is required to align its building blocks into its structure. Spacetime's structure provides the means for the properties of distance and 3 spatial dimensions to emerge. The next question at hand is, what is the speed of light? To understand what the speed of light is, we'll use an ideal one-dimensional universe consisting of a linear arrangement of stationary building blocks that are equally spaced apart. Each space represents a quantum distance, and the energy density is the same everywhere along the line. Let's imagine what would happen if we moved the building block along the line and brought it back to rest. Moving the building block requires energy, and this energy will dissipate along the linear energy medium in the form of a compression wave. At what speed do you think the wave of energy will move along the one-dimensional energy medium? You guessed it, it's the speed of light. But what is the speed of light, and how do we define it in terms of this model? Hierarchy of energy theory defines the speed of light as the speed at which energy moves through an energy medium. The speed is defined as 1 quantum distance per 1 quantum time unit. But wait, what's a quantum time unit? And where did that come from? A quantum time unit is just the time it takes for an energy wave to traverse a quantum distance. That seems simple enough until you consider that we found the quantum distance to be relative. The quantum distance is relatively shorter when the energy density along a spacetime path is higher, and it's relatively longer when the energy density along a spacetime path is lower. The fact that the quantum distance is relative to the energy density of spacetime does not change our definition of the speed of light. Our definition remains the same. The speed of light is a quantum distance divided by a quantum time unit. The only way the speed of light remains the same is to not only have the quantum distance being relative to the energy in spacetime, but the quantum time unit must also be relative to the energy density in spacetime. And more importantly, the relative quantum distance and the relative quantum time unit must both change in the same proportions in relation to the energy density in spacetime. Since the speed of light is the ratio of the relative quantum distance over the relative quantum time unit, the speed of an energy wave in the spacetime energy medium does not change as the wave moves through the regions of spacetime with different energy densities. Let's take a closer look at a wave moving through regions of spacetime with differing energy densities. When we observe the speed of an energy wave from a perspective outside of spacetime, we see that a region with twice the energy density would have twice the number of quantum distances and twice the number of quantum time units. We would observe the wave speed in this region as moving at half the speed compared to the region of spacetime with half the energy density. But wait, didn't we just say that all waves in spacetime move at the speed of light no matter what the energy density is along the path? What gives? Well, I'll tell you what gives. When we put ourselves in spacetime, in a region of spacetime with a lower energy density, we will measure the speed of an energy wave moving towards us at a quantum distance per quantum time unit, or the speed of light. Now let's put ourselves in a region of spacetime with twice the energy density, twice the number of relative quantum distances, and twice the relative quantum time units. We will still measure the speed of an energy wave moving towards us at a quantum distance per quantum time unit, or the speed of light. The fact is that we cannot tell the difference between the speed of these waves when measuring them from within the spacetime energy medium. This demonstrates the concept of the relative constant, where the speed of light is a relative constant. It is always measured at the constant value within any region of spacetime we are in, and yet it is relative to the amount of energy within the region of spacetime it is moving through. This solves the problem I call the concept of infinite scales. The speed of light could be any value between 0 and infinite, and from a perspective outside of spacetime, it could actually have any value between 0 and infinite. But because of the nature of the energy medium, the measured value of the speed of an energy wave measured from within spacetime is always measured at the same value, a quantum distance divided by a quantum time unit. That is the speed of light. I would be amiss if I didn't mention the famous Michelson-Morley experiment that supposedly proved that there was no medium. This was not an unreasonable conclusion considering the mindset of what was considered a medium at the time. But the space-time energy medium is unlike any medium we've ever encountered, where this medium actually determines the relative distance and relative time emerging from it. Michelson-Morley's experiment showed us that moving in spacetime does not change the measured speed of light. But it didn't tell us why. As mentioned before, we shouldn't look at spacetime as a structure of measuring rods and clocks. We should look at spacetime as a structure composed of energy, where energy densities determine the relative distance and relative time along a path in the medium. Let's look at this another way. What if our spacetime had different energy densities along the independent energy directions? If the measured speed of light varies with energy density, then looking in different directions would result in the speed of light being different in these directions. And that would be a crazy universe indeed. For the speed of light to be the same in all directions, there is either no medium, as concluded by the physicists after the Michelson-Morley experiment, or there is a medium where the speed of light is a relative constant. But wait, there's more. Moving in spacetime means we are in a moving reference frame, and we can say that spacetime is relatively moving with respect to us. Moving spacetime has a greater energy density compared to non-moving spacetime. But now we found that the speed of light doesn't change when observing it in our moving reference frame. And that's because no matter what the underlying energy density is of our underlying spacetime, the speed of light has to be the same value. This is the basis for Einstein's postulate used to derive the theory of special relativity, that being the speed of light is the same in all inertial reference frames. Hierarchy of energy theory finally gives a real solution why this postulate is true, other than a physicist or my mother telling us, "Because I said so." Not an answer. When taking my college physics class and learning that light was a wave, I asked my professor, what is the medium that the wave moves in? He said, there is no medium. And I said, bullshit. There's got to be a medium because the light has the same mathematics as all waves. And all waves have mediums. Well, we found the energy medium of spacetime, but what about the mathematics of a wave in this medium? It turns out that an energy wave in spacetime follows the exact same wave equations that we are familiar with. And in the case of spacetime waves, they are longitudinal compression waves. Physicists and engineers will recognize this equation. In deriving the wave equation for a wave in spacetime, it's completely analogous to the derivation of any compression wave. This derivation is well established, but there are a few alterations required when applying it to a wave in spacetime. We need to represent the mass in the equation F equals ma as energy density along the spacetime path. The final result is that the standard wave equation is the same for a wave in spacetime. Let me say now, I am not here to teach well-established physics. The physicists should already know it, and I don't want to bore anyone to tears while watching these videos with detailed mathematical derivations. However, I would like to point out that in the derived spacetime wave equation, the velocity of the wave is contained in the equation. It is expressed as the square root of the ratio between the modulus of elasticity of spacetime divided by the spacetime's medium's energy density. If the speed of light is the same no matter what the spacetime's energy density is, it means that spacetime's modulus of elasticity changes in proportion to the energy density of spacetime. But does this proportionality hold up? Well, let's see. If we double the energy density of spacetime, we double the number of quantum distances. Each quantum distance would be half its original length. To compress or stretch a higher energy quantum distance to the same percentage, it would require twice the force. And this correlates to doubling the modulus of elasticity. Therefore, doubling the energy density of spacetime also doubles the modulus of elasticity, thus keeping their ratio the same value. So again, the velocity of an energy wave moving through spacetime is measured at the same value no matter what the energy density is of the underlying spacetime. In wrapping up this lesson, we could easily extend the principles of an energy wave moving along the one-dimensional spacetime to a three-dimensional spacetime medium to represent energy waves as they exist in our spacetime. In summary, the speed of light is a relative constant. The relative constant is a new concept introduced to the field of physics by hierarchy of energy theory. The relative constant solves the concept of infinite scales and tells us why our physical constants have specific values when they are measured within our region of spacetime. An energy wave in spacetime follows the same mathematics as any wave moving through a medium. So far, we have shown that the speed of an energy wave moving through spacetime moves at the speed of light. But this wave is an energy wave of the spacetime energy medium. It is not what we know as a light wave or a photon. An energy wave of spacetime is like a wave in the ocean. Its energy will eventually disperse as the wave evolves into little ripples and it spreads into the medium. But a photon is a package of energy which does not disperse into the medium. Its energy somehow remains intact and stable as it moves through spacetime. So how does the energy of a photon maintain its quantum energy level as it moves through spacetime as a wave? This is the next Nobel Prize winning topic of our next video. If you are curious about this novel approach to finding the theory of everything, then click the like button below and subscribe to this channel so that you can be notified when future lessons are released.